Alright, so this is problem 3 from homework 5 part 2. And so the problem asks to state and prove a generalization of a result that is apparently well known, that if you add up, that if a number is divisible by 9, then the sum of its base 10 digit is divisible by 9, and vice versa, right? Since it's a if and only if statement. So if you add up the base 10, if you add up the digits, it is divisible by 9, and if it is divisible by 9, then the sum of the digits is also divisible by 9. And so yeah, let's see what that means. So just as they tell us, they say base 10. So we're working base 10, and if we have a number like 16,452, if we add up its digits, so 1 plus 6 plus 4, that looks like a B, plus 5 plus 2, we get 18, sorry. And we know that 18 is divisible by 9, right? Since 18 divided by 9 is 2, which is an integer. And so if this theorem was true, that would mean that then this number is also divisible by 9. So let's check. So 452 divided by 9 is indeed equal to an integer, which is 18,028. So it seems like, at least for this number, that holds true. And let's see what that means when we take it for any base. So let's do base 16, for example. So in base 16, we can have, for example, this number, f69a5. And if we add up its digits, you can see we have f plus 6 plus 9 plus a plus 5. That's equal to 2d, which is 45 in base 10. And so 45 in base 10, so 2d is divisible by 9, right? 2d divided by 9 is equal to 5. However, if we take the number that we got, f69a5, if we divide that by 9, we'll actually get a fraction. We'll get 1b667 plus 6/9. So we can see that doesn't hold true for other bases, and that means that instead of having 9 here, we'll actually have b minus 1, and we'll see that will work. So if we do base 16 again, and we do another example, but now we'll check if it's divisible by b minus 1 instead. So in this case, b minus 1 equals f. So if we have this number, 5ba3c4, we can see that it's the sum of its digit, 5 plus b plus a plus 3 plus c plus 4, is equal to 2d, and which is also 45, right, from before. And 2d divided by f is 3, which is an integer. So that means that the sum of these digits is divisible by f. And if we check the number, 5ba3c4 divided by f is also an integer, which is in this case 61bfc. Okay, so now we know what we're talking about, right? We want to prove that in any base b, if the sum of the number of any number is divisible by b minus 1, then the number itself is divisible by b minus 1, and vice versa, right? Since it's if and only if. So what we need to prove then is that So numbers, we write them like this, right? We say that n is equal to a j, ak times bk plus ak minus 1 times bk minus 1, and etc. until a 0, b0. So I'll just write that as the sum of j is equal to 0 to k of ak, aj, b to the j, my bad. And I won't write out the j equals 0 to k on the other sigma signs, just for time's sake. But yeah, that's what we mean when we say that this number, yeah. So what we need to prove is that if we have aj, if we have the sum of the digits is divisible by b minus 1, that implies, and that's because of the if and only if, it goes the two ways, that implies that that is going to be true if and only if the sum of the actual number is divisible by b minus 1, which is, as we saw, aj times b to the j. All right. So if we convert that to modulus algebra, using the definitions that we had, we get this transforms into the sum of the digits is congruent to 0, and modulus of b minus 1. And so that would be true if and only if, I'm a little tight on space, if and only if the actual number is congruent to 0, modulus of b minus 1. All right, so this is what we need to prove. And so the first thing I'm going to do is to recognize that b is congruent to 1 in modulus b minus 1, right? So that's because b is 1 more b is equal to b minus 1 plus 1, right? B is 1 more than b minus 1. So yeah. Then that would mean that b to the j is equal to 1 to the j, because we know that b is congruent to 1. So this is congruent, right? And I'll put it here. It's congruent to 1 to the j, which itself is congruent to 1 in mod b minus 1. So yeah, hopefully that makes sense. We know that b is congruent to 1 in mod b minus 1, and so that means that we can substitute 1 here for b, and so we get 1 for any b to the j. So for example, that would mean that in base 10, if we have 10,000, for example, and we divide that by 9, we should get some number and a fraction 1 over 9, right? And that's true, right? Because it's 999, it's 1 plus 199, 999. Okay, so then proving that, having proved that, we can replace this part here by 1, so we can say b2, the sum age, the sum of basically the number is congruent to the number, the sum of the digits times 1, right? Because we can substitute 1 for this, and that will be congruent to the sum of the digits in mod b minus 1. And yeah, here we prove that in mod b minus 1, the number is congruent to the sum of the digit. So we have, so now we know that if for example here, the sum of the digit is congruent to 0, then that will have to mean that the sum of the digit times the multiplier is also congruent to 0, since we proved they're equal, right? We proved that aj is congruent to aj b to the j in mod b minus 1. And also, it goes the other way around. If the number is congruent to 0 mod b minus 1, then the sum of the digits is also congruent to 0 mod b minus 1. And we can write that like this. The sum of the number congruent to 0 implies that the number is congruent to 0 and in the mod b minus 1. And we can also see that the opposite applies, that if the number is congruent to 0, then the sum of the numbers is congruent to 0 too. And so yeah, we proved the implication both ways. So that means we can say that the sum of the numbers is congruent to 0 if and only if the number is congruent to 0 in mod b minus 1. And that's what we wanted to prove, right? Right here. So yeah, we proved that the sum of the digits, if the sum of the digits, any number in any base is divisible by the base minus 1, if and only if the sum of its digits is equal to the base minus 1. All right, thank you.